This is the second part of Chapter 2, Rotational Spectra of Diatomic Molecules. In the previous part, we have started studying the rotation of a diatomic molecule classically. After that, we moved to treat this rotation quantum mechanically, and we ended up writing a formula that describes the energy of these energy levels, or the rotational energy levels. It was found that quantum mechanically, the energy levels or the energy is quantized. It is a function of a quantum number J. After that, we have described two terms, or we introduced two terms, which are the spectral term and the rotational constant. Now, after defining rotational energy levels, let's see if all transitions from any level to any level is possible, or there are rules for these transitions. For a molecule to be able to absorb or create a photon of frequency nu, it must possess a dipole oscillating at that frequency. So there must be a dipole oscillating in the molecule at the frequency nu, the frequency of the emitted photon or the absorbed photon. What is a dipole? An electric dipole deals with the separation of the positive and negative electric charges found in any electromagnetic system. A simple example of this system is a pair of charges of equal magnitude but opposite sign, separated by some distance, for example d. So if we have here a charge, positive charge plus q, and here a negative charge minus q, separated by a distance d, the dipole is defined mu equals q times d. Charge multiplied by the. This is the classical expression of a dipole. نحن بنعرف إنه إذا عنا diatomic molecule ممكن الاثنين atoms تاعولها ما يكون عندهم نفس electronegativity. What is electronegativity? It is the ability of an atom to draw electrons to itself. يعني تشد لعندها الإلكترونات. فبالحالة اللي بيكون عندي فيها heteronuclear molecule يعني الاتومز مش مثل بعض، فأكيد عندهم different electronegativities، رح يكون واحدة منهم عندها tendency to attract electrons more than the other. So one will attract electrons and one will partially lose electrons. So رح نشوف إنه we will obtain a center of positive charges and a center of negative charges, and this creates a dipole in a diatomic molecule. So بصير في جهة عندها تقريبا partial loss of charges وجهة partial gain of charges. So جهة راح تكون positive جهة راح تكون negative, and this is the origin of a dipole. Now how to deal with this dipole quantum mechanically? In quantum mechanics, we use the term transition dipole moment. We care about the dipole moment between an initial state and the final state. So we calculate mu fi, which is the integral of psi f, which is the final state, star mu psi I, where mu is the electric dipole operator. So we have to calculate this term, which describes the transition dipole moment. A transition will be active, so the transition is possible only if this transition dipole moment is not zero. So as you can see, the condition is that this transition dipole moment must not be zero, so that the transition from the initial state I to the final state f is possible. The wave functions of rotational energy levels are already calculated quantum mechanically, so we can insert psi initial, psi final, and the value of the electric dipole moment operator, which is q times r or d. I'll try to solve the integral to check if it is zero or not, and to guess if this transition is possible or not. Or we can substitute for psi I and psi f, substitute for their values in general, and then try to find a formula or a rule such that applying this rule guarantees that the transition from this initial state to this final state is possible. This is called the selection rule. So once calculating the transition dipole mu fi, it can be regarded as the measure of the charge redistribution that accompanies a transition. So mu fi in reality It measures how did the charge redistribute in the molecule when the molecule passed from this initial state to this final state. إذا في تغيير بالcharge، إذا في redistribution للcharge، يعني في transition، يعني transition is allowed. إذا ما في redistribution للcharge بتبقى شكل الcharge مثل ما هي، توزيع تعولها مثل ما هو رح يبقى، لكن بهيدي الحالة ما في transition. The transition is not allowed. So, the gross selection rule for the observation of a pure rotational spectrum is that a molecule must have a permanent electric dipole moment. So, condition 1, the molecule must have an electric dipole moment. So, this is only true if we have a polar molecule. A polar molecule, it means that a molecule in which the center of positive charges is different from the center of negative charges. It has a dipole. This is true for any heteronuclear nature molecule, but not true for a homonuclear diatomic molecule. So لما يكونوا الاثنين atoms different, it's polar because one of them will be more electronegative than the other. لما تكون homonuclear, for sure they will have the same electronegativity and we will have no dipole. The dipole is zero. So what do we deduce? We deduce that a heteronuclear diatomic molecule has a rotational energy spectrum, while a homonuclear diatomic molecule does not have a rotational energy spectrum. If it doesn't have a rotational energy spectrum, I'm talking about homonuclear diatomic molecules. It doesn't mean that these molecules cannot rotate. They can rotate, but we cannot see or we cannot distinguish the rotation in the form of a spectrum. So here on the right, you can see a molecule, a heteronuclear molecule with different atoms rotating, and you can see the dipole. So this is the dipole mu. This is the dipole mu. You can see it. The dipole is rotating, and this rotating of the dipole will create the possibility of absorbing or releasing a photon. So to a stationary observer, a rotating polar molecule looking like an oscillating dipole that can steer the electromagnetic field into oscillation, and vice versa for absorption. This picture is the classical origin of the gross selection rule for rotational transitions. So the first rule, the molecule must be polar, heteronuclear diatomic molecule, because we are talking only about diatomic molecules. You can see that we always start from classical mechanics to arrive to quantum mechanics. Classical mechanics is always important in understanding things. Now let's find these rotational selection rules. How to find them? As I have said earlier, we go to the transition dipole moment quantum mechanically, we substitute for the wave functions, and we check for what values mu fi is different from 0. So for a linear molecule, for a diatomic molecule, they have found that the transition dipole moment is different from 0 when delta J is equal to plus or minus 1. This is the condition. If delta J is equal to plus or minus 1, that means delta Mj is 0 plus or minus 1. Now, delta J equals plus 1 corresponds to an absorption of a photon. Delta J equals minus 1 corresponds to the emission of photon. This is due to the conservation of angular momentum. So, we know that a photon is a spin 1 particle. So, if the molecule absorbs a photon, its momentum must increase 1. If it loses a photon, its momentum must decrease 1. That's why delta J is equal to plus 1 in absorption and minus 1 in emission. Here in the adjacent figure, you can see that we have a molecule rotating, and after the absorption of a photon, the angular moment of the molecule, the new total angular momentum, is equal to the old angular momentum plus the spin of the photon. So when a photon is absorbed by a molecule, the angular momentum of the combined system is conserved. If the molecule is rotating in the same sense as the spin of the incoming photon, then J increases by 1. We have studied that rotational selection rules include the molecule or the diatomic molecule must be heteronuclear, it must be polar. And the second condition or the second rule is that delta J between the levels must be equal to plus or minus 1. Delta Mj for sure is equal to 0 plus or minus 1. Now, after discussing the selection rules, let's take a look at the appearance of the rotational spectra. So the allowed transitions for the absorption are from J to J plus 1. Because we have said delta J is equal to plus 1, that means we are able to move from J to J plus 1 in the case of an absorption spectrum. In this case, the wave numbers, when we move from J to J plus 1, are equal to Fj plus 1 minus Fj, already calculated, to be 2Bj plus 1, already calculated in a previous slide, in a unit centimeter minus. If the wave number is equal to 2Bj plus 1, where B is a constant, already discussed earlier, then you can see that V is similar to the empirical formula seen in the beginning of this chapter, where we have assumed that V is equal to some sort of a constant A multiplied by an integer. So you can see if J is an integer, then J plus 1 is also an integer, which replaces M. And here, there replaces 2B. Now the wave numbers are for J equals 0. So if we are moving from J0 to J equals 1, we will get 2B. If we are moving from J equals 1 to J equals 2, well, I'm just substituting for J here. Okay, so we substitute for 1 and we will get 4B. And now if J is equal to 2 to J equals 3, we substitute in the same equation for J equals 2 and we will get V bar equals 6B. So this is the first transition from the first level to the second level. It has a frequency or a wave number 2B bar. The second one has a wave number 4B bar. The second one has 6B bar, etc. We see lines and the spacing between these lines is equal to 2B, where B is the rotational constant. If we are able to find B using the spectrum of a certain molecule, remember that B depends on the moment of inertia of the molecule. So if we know B, we are able to calculate I, the moment of inertia. If we calculate I, we are able to calculate the bond length of a diatomic molecule if we know the masses of the atom. One more note before ending this slide is that there is a maximum intensity here. The intensity of the line is not the same everywhere. They are not equal. So a higher intensity corresponds to a higher or is related to a higher population of rotational levels. So it means that there is a higher number of molecules occupying these energy levels. This is one of the causes of this high intensity in this region. بس لأكد على شغلة mu bar هي الويف نمبر يلي عم ينعمل له absorption. So لما أنا أشوف السبكتروم عم شوف absorption على هيدول الويف نمبرز أو هيدول الفريكونسيز. هيدول الفريكونسيز عم يصير لهم absorption. We have said that one important reason for the maximum intensity is the existence of a maximum in the population of rotational levels. So بيكون في عنا levels occupied more than other levels, which creates or which affects the maximum intensity in the rotational spectrum. Now this population is studied using Maxwell-Boltzmann distribution. Any atom, ion molecule, particle that has a set of states occupies these states according to Maxwell-Boltzmann distribution. The number of particles in each level is called a population. So the population is the number of molecules that occupy this energy level. And this population follows the Maxwell-Boltzmann distribution. What does this law say? As it appears clearly, so Ni over N0 equals Gi over G0 exponential minus Ei E0 over kBt. So Ni is the number of particles in a certain state I. N0 is the number of particles in the ground state. Gi is the degeneracy of state I or level I, while G0 is the degeneracy of the ground state level. Ei is the energy of the level I, and E0 is the energy of the ground level. Kb is the Boltzmann constant, and T is the temperature in Kelvin. So we can know the percentage of particles that occupy a certain energy level I with respect to the particles that occupy the ground state. Now let's apply this distribution or Maxwell-Boltzmann distribution to our case, where we know very well the degeneracy of each level. Let's consider the rotational energy level Ej and the ground level E0. So their degeneracies Gj equals 2j plus 1, and here it's also 2j plus 1, but we substitute for j0 because it is the ground level, so we get 1. Applying Boltzmann distribution, we get this is 2j plus 1, and this is 1. We get Gj exponential, and the energy for sure is considered to be 0. Remember that Ej equals Jj plus 1 h bar squared over 2I, so E0 will be equal to 0 if we substitute for J0. That's why we have cancelled the ground state energy. Using this relation, it is shown that at ordinary temperature, several levels of rotation are populated. In absorption experiment, we must expect transitions starting from energy levels corresponding not only to J equals 0, but also higher values to be important. Let me explain this in a different way. We see that the ratio of the number of particles occupying the level of energy Ej over the particles occupying the ground state level is equal to Gj exponential minus Ej over kBt. As we go up higher to higher values of J, to higher energy levels, we have no problem with the Gj. Gj will increase. We care about the ratio Nj over N0. Will our ratio increase? If the ratio will increase, it means that more particles are likely to be occupying these levels of quantum number J. If the ratio is going to decrease, it means that less particles are occupying this level or this rotational level of a quantum number J. So we have no problem with the Gj. Gj is increasing anyway. As J goes up, Gj will increase. Our problem lies with the exponential part, because as J goes higher, the energy will increase, but we have a minus sign in front of the energy, so exponential minus positive value will decrease, which affects the total ratio Nj over N0, which will decrease. You know from math that the exponential function e minus x, for example, for small values of x, so if x is small, then ex is, okay, so it has certain values, it's not 0 yet, okay, it does not arrive to 0 yet. But as x tends to increase, e minus x decreases till it reaches 0. Approximately for x equals 5, we will get e minus 5 approximately equal to 0. Here in our case, the ratio of Aj over kBt for small values of j, let's say for the first few values of j, is not big enough so that the exponential tends to 0. Approximately at ambient temperature, this corresponds to 200 centimeter minus 1. It corresponds to a wave number of 200 centimeter minus 1, which is comparable with the rotational energy of molecules. So the ratio Ej over kBt is not very large yet, so we can see the first few rotational levels occupied at ambient temperature. Now, why does this happen physically? Why do we find molecules occupying energy levels with values of J higher than 0? It's simply because when molecules absorb the thermal energy, which is kBt, they can do a transition from one energy level to another because the energy or the thermal energy kBt is enough for them. The spacing between the levels is very short, it's very small, so a molecule can move from one level to the other, only depending on the thermal energy. The second note says the population of each state decays exponentially with increasing J, but the degeneracy of the levels increases, and these two opposite trends result in the population of the energy levels passing through a maximum. As you can see, a Gj always increases. The exponential part will decrease. So there are two effects opposing each other, one increasing, the other decreasing, which results in a maximum. So that's why when we look at the rotational spectrum of molecule, we observe a maximum in the intensity of particles. نشوف maximum لأنه في عنا particles بالعادة populating هيدول levels أكتر، فلكن بصير في emission للفوتونز أو بصير في absorption للفوتون بهيدا المطرح أكتر لأنه في particles absorbing أكتر. Now how to find which energy level has the highest population? It's easy. We take our function, which is the ratio nj over n0, which is a function of j. We treat this function as a continuous function. It's not continuous because j is discrete already. It's an integer, but we treat it as if j is a continuous variable and our function is a continuous function. We do the derivative. We put our derivative equal to 0. We search for this maximum and we try to find j. Once finding j, we will get for a linear rotor that j maximum equals radical kbt over 2hc b bar minus half. So I will prove this formula in the exercises later and how to find it using Maxwell-Boltzmann distribution. One last note about this is that this is the maximum or the highest population, j of the highest population. That means the j that contains or the level that contains the highest number of molecules or the highest number of molecules that have this quantum number j or this energy level ej. But usually when we look at the spectrum, not all the time for all molecules, the highest intensity corresponds to this j max. Why? Because there are other factors that must be taken into account. Not only the intensity of the spectrum depends on the population, but it also depends on the transition. It depends on the population difference between the two states of transition. It depends on a mu. We're not going to go deeply through this. It's not required. We only have to know that there are levels more populated than other levels and how to calculate this population or how to find the level that is the most populated. The value of j corresponding to the most intense line is not quite the same as the value of j for the most highly populated level. As I have already explained, the intensity of a transition or the intensity of a peak or a line in the spectrum depends on the population of levels and also depends on something else, which is the population difference between two states of transition. So two things control the maximum intensity in the spectrum. Not always the highest line corresponds to the mostly populated level. Let's check this example. Let us determine the population distribution for the rotational energy levels of the molecule HBr with the internuclear distance r equals 0.141 nanometer. So we are going to calculate the ratio nj over n0 using Boltzmann-Maxwell distribution. As we have already seen, nj over n0 is equal to 2j plus 1 exponential minus ej over kbt. Substitute every term for its value. We have to find ej. ej is equal to hc b bar j plus 1. To be able to write ej, we have first to find b. So b bar, it's equal to h bar over 4 pi ci. So h bar is a constant, c is a constant, there's left I. So we have to find I. The first step is to find the moment of inertia of the molecule. Once finding I, we can find b. Once finding b bar, we can find ej. Once finding EJ, we can substitute the expression of EJ in the Maxwell-Boltzmann distribution, and we get our function Nj over N0 as function of J. And we can substitute for J and find any population or any percentage we want to find. Let's find I together. I equals mu r squared for a diatomic molecule. Mu is the reduced mass. It's equal to the multiplication of the masses over the sum of masses of atoms of the molecule. So mH times mbr over mH plus mbr. We can find the masses here. This is the atomic mass. This is 1, this is 81, and this is 1, this is 81. Now to deal with the mass, there are two methods. I will teach you both of them. First, they must be substituted in atomic mass unit because you are dealing with only one atom of hydrogen, one atom of Br. So the real unit is AMU, atomic mass unit. So we can't keep them in this unit, AMU. We have to change them to the SI unit, which is kilogram. So to change from AMU or AU to kilogram, we have to multiply by 1.66 times 10 to the power minus 27. This ratio here, mH mbr over mH plus mbr, has a final unit AMU, and then we multiply by 1.66 times 10 power minus 27. It is now in kilogram. R squared is in a nanometer. It must be substituted in meters, so it's 0.141 times 10 to the power minus 9. We substitute, we solve, we get our I. This is the first method. The second method is that it's the same, but just a small alteration, is that substitute for the masses of a mole. So for a mole, we have 1 gram, it's 1 gram. This is 81 gram, and this is the same 181, but the final unit will be gram instead of AMU because we are talking about a mole and not a single atom or single molecule. We are talking about a mole of molecules. So to change it to SI unit, anyway, this is the ratio. To change it to SI unit, we have to multiply by 1 over NA, 1 over Avogadro's number. Why by 1 over Avogadro's number? If we are finding the reduced mass, نقسم على ال NA اللي هي عدد الموليكولز بالمول الوحدة، بيطلع أنا عندي الموليكول الوحدة قد عندها reduced mass. So إذا أنا بعوض بالجرام، أنا بكون عم جيب reduced mass لمول. بقسم على NA, which is the number of molecules in 1 mole. بس اقسم على NA بيطلع أنا معي reduced mass for 1 molecule. So we get our answer, but كمان our answer is in gram. So 1 times 81 over 1 plus 81. أكيد we have to multiply by 10 to the power minus 3 to get it in kilogram. وبنرجع بنقسم على Avogadro's number, which is 6.022 times 10 to the power minus 23. So it will give the same answer. Now we have calculated I, we have to calculate B bar or B. So B is equal to H bar over 4 pi Ci. So H bar is Planck's constant over 2 pi, it's H over 2 pi. H is usually given in the exercises, it's a given constant. C is the speed of light, it's also a constant, and I is already found. Substitute, you will get 858 meter minus 1. If everything is substituted in SI unit, we will get B in meter minus 1. Now, let's substitute B, or the value of B, in the expression of EJ. H, we have it, it's a constant, it's Planck's constant. And C is also a constant. It's 3 times 10 to the power 8. C equals 3 times 10 to the power 8 meter per second. Planck's constant H is equal approximately to 6.626. These are given usually in the exercises. Times 10 to the power minus 34 meter square kilogram per second or joule second. So substitute H, C, their values, the value of B bar, you will get this number. we keep J as an arbitrary quantum number. So now we substitute everything for its value. Here we have Ej over kBt. We have the expression of Ej already calculated. It is 1.706 times 10 to the power minus 22 over kb. It's also a constant. It's 1.38 times 10 to the power minus 23. And T is the temperature in Kelvin. If we are at ambient temperature, it will be 25 plus 273. So this is the temperature. So we get this final expression for the population distribution. Now let's take a look on this diagram here, which shows the energy levels and the population. This gives Nj over N0. So the first one is 1 because for sure N0 over N0 will be 1. And if we substitute for J equals 0, we will get 1. Then this corresponds when we substitute in this expression, J equals 2. And you can see that the population in level 2 is more than the population in level 1. Or for J equals 1, this is J equals 1, the population is higher than J equals 0. Now for J equals 2, the population is higher, and for J equals 3, the population is even higher, and then for J equals 4, the population starts to decrease. So as you can see, we have a maximum, and then the function starts to decrease again. We can deduce that for J equals 3, or J equals 3 is the level that has the most population. We can deduce that J equals 3 is the level that has the most population. So we can expect that around J equals 3 will be the highest intensity of the spectrum. So here the highest intensity is approximately around J equals 3. Or a transition from 2 to 3 and from 3 to 4. Let's take a look on this diagram on the right. This diagram gives the ratio Nj over N0, which corresponds to the population of levels. The first one corresponds to J equals 0. So we substitute J equals 0 in the expression of Maxwell-Boltzmann, and we will get 1 for sure. The ratio N0 over N0 will be 1. This is the ground level. So for J equals 1, we have a ratio Nj over N0 equals to 2.76, which means that this level is more occupied than the level J equals 0. And then for J equals 2, we have a population of 3.9, which is even more occupied than 1 and 0. And J3 has the highest population as it appears, it's 4.25. Then after J equals 3, we will get a smaller population, 3.98, which corresponds to J equals 4. So we deduce that we have a highest population that is at J equals 3. So it means that this level with a J equals 3, with the quantum number J equals 3, is the most populated, contains the highest number of molecules. Here Gj corresponds to the degeneracy. This is the degeneracy. This is 1, 3, 5, 7, 9, etc. And here is the energy in terms of wave numbers. We have already explained that earlier. So it's 0, 2b, 6b, etc. Due to the population, we will get some sort of lines where the maximum is in the middle, around J equals 3. This is the rotational spectrum for HBr molecule. As you can see, the distance between two successive lines is approximately equal. So finding this distance, we can calculate B bar. Once calculating B bar, we are able to calculate I, because B depends on I. And once finding I, if we know the masses, we can calculate R, which is the internuclear distance. So if we have a spectrum for a molecule, we are able to calculate their internuclear distance. Up till now, we have only considered a rigid rotor. What is a rigid rotor? A rigid rotor is a molecule or a diatomic molecule in which the bond length is constant. It is considered constant while the molecule is rotating. But this is not true if we are considering a real rotor. If we have a real rotor, the bond length between the two atoms forming a diatomic molecule will increase due to the centrifuge force. When the angular velocity of rotation increases, the centrifuge force, so F centrifuge, it depends on omega, will increase. So when the centrifuge force increases, the internuclear distance will increase. So when the internuclear distance increases, the moment of inertia will also increase. So if the moment of inertia increases, then B will decrease because B is inversely proportional to I. If B decreases, you know that the spacing between the spectral lines depends on B. So if B decreases, the separation or the spacing between the spectral lines will decrease as J increases or for higher values of energy. So if we are going to consider a real rotor instead of dealing with a rigid rotor, we have to talk about the centrifugal distortion. The distortions that are caused by the centrifugal force. So as you can see here from the figure aside, when the molecule rotates, the bonds will stretch according to the centrifugal force. So this is not a diatomic molecule, but for a diatomic molecule, things will be the same. The molecule will stretch and the radius will become larger. The centrifugal force arising from rotational distorts the molecule, opening out bond angles and stretching bonds slightly. So stretching bonds means that R will increase. The effect is to increase the moment of inertia, so I will increase of the molecule, and hence to decrease its rotational constant, we mean that B will decrease, and constantly the energy levels are slightly closer than the rigid rotor expressions predict. So if B is smaller for higher values of J, so the difference or the distance between two lines or two levels will be closer or smaller. The effect is usually taken into account largely empirically by subtracting a term from the energy and writing. So this is the energy of as a wave number, energy expressed as a wave number for a rigid rotor, and this part is called the centrifugal distortion, which is due to the centrifugal force. The parameter d, J, is called the centrifugal distortion constant. It is large when the bond is easily stretched. In the molecules where the bond can easily stretch, it is small when the bond is hardly stretched. So D is very small in comparison with B. It's a small correction. Approximately D is 10 to the power minus 4B. For a diatomic molecule, the centrifugal distortion constant, which is D, J, is related to the vibrational wave number of the bond nu bar through the approximate relation dj equals 4b cube over nu bar. So I will prove this formula and this formula, both of them, in an exercise later at the end. So how do we arrive for a diatomic molecule to see this formula? Now, due to the centrifugal distortion, we have a change in the energy of a rotational energy level, and hence we have a change in the frequencies or wave numbers of the allowed transitions between these rotational energy levels, because we are no more using or no more considering a rigid rotor. We are considering a real rotor, a non-rigid rotor. So as you can see, nu bar, the frequency or the wave number of absorption for a transition between the levels or from the level of quantum number j to the level j plus 1 is equal to fj plus 1 minus fj. Fj was already shown in the previous slide, so to find fj plus 1 we have only to substitute, instead of j we substitute j plus 1. So we will get, this is fj plus 1, and this term here corresponds to Fj. So let me just erase. Okay, so let's take these two elements together. Take as common bj plus 1. There remains j plus 2 minus j. So as you can see, these are cancelled. We are left with 2b bar j plus 1. And this corresponds to the first term. Now let's do the second term with the fourth term. Let's take as common minus d bar j plus 1 squared. So we are left with j plus 2 squared minus j squared. So this is a difference of two squares. It is j plus 2 minus j and j plus 2 plus j, which is equal, this is equal to 2, and this is equal to 2j plus 2. So we are left with these. So this is 2, and here we have 2j plus 1. At the end, we arrive to 4j plus 1. So this term here is 4j plus 1. This term here is 4j plus 1. So we end up with minus dj 4, there's a term 4, j plus 1 cube. And you can see it's the same as here. So it's minus 4 dj j plus 1 cube. Now let's calculate the relative correction. How much is this correction for a given value of j? الريلاتيف correction هي نسبة التصحيح، يعني قد ايه غيرنا بالويف نمبر مقارنة مع القيمة الأساسية تاعية الويف نمبر. يعني لما نحن دخلنا هالسنترفيوجال ديستورشن قد ايه تأثيرها على قيمة الويف نمبر. The relative correction for a given value of j, delta f j over f j. Delta fj is the centrifugal distortion or the correction that we have added, which is dj j squared j plus 1 squared over fj, which is the initial value of the wave number when we were dealing with a rigid rotor. It was bj j plus 1. So j with j cancelled, j plus 1 with j plus 1 cancelled, we are left with d bar over b bar j plus 1. And as you can see, we have the same result as here. This ratio shows that this correction is very, very small. It's never high unless we reach high values of j, high rotational levels and very high rotational levels. For example, for HCl molecule, this ratio is only 4% even if j is 20. 20 is considered a high rotational level. And it's 9% for j equals 30. For HCl molecule, dj is approximately equal to 0.5 times 10 to the power minus 4b. It's approximately 10 to the power minus 4b. It's small in comparison with b. And for small values of j, it's negligible approximately. It's never important unless we reach very, very high values of j or high values of rotational levels. هلأ هو اعتماد الريجيد روتور موديل بأول تشابتر ما كان سيء أبدا، وخاصة for small values of J، لأنه أعطانا فكرة واضحة عن الانرجي ليفلز، عن الفريكونسيز، عن البي كيف رح تكون، وكتير هي هيدي الفاليوز قريبين على الريل فاليوز. بس لما نصير على الهاير ليفلز ممكن يصير في شوية فروقات ما بين الريل ليفلز والليفل levels calculated using the rigid rotor model. So using the rigid rotor model was not that bad at the end. But for sure, the non-rigid model is more precise. So the centrifuge distortion correction is obviously observed for high rotational energy levels. Therefore, measurement instruments of very high resolution are to be used in this case. So as you can see here, there is a difference on this diagram to the right between the energy levels in case of considering a rigid rotor and the case where we have considered a non-rigid rotor or a real rotor. You can see the difference between rigid rotor and non-rigid rotor. For the first few levels, 0, 1, 2, 3, 4, 5, 6, Okay, and there's a little bit of difference between the levels of rigid rotor and non-rigid rotor. When we reach 7, 8, you can see that the non-rigid rotor levels are lower than the rigid rotor levels. So you can see that the difference between them starts to appear. So the effect of centrifugal distortion shown by the comparison of the allowed rotational energy levels of a rigid and non-rigid rotor. So this is a comparison between both of them. So this table here gives the observed wave number for a transition from the level J to J plus 1. Here using the rigid rotor formula to be J plus 1, and here using the non-rigid rotor formula with the correction. So you can see the observed or the experimental value for a transition from 3 to 4 is 83.03. Using the rigid rotor, it is 82.72, and using the non-rigid rotor, it's 83.06. It's very, very close to the experimental value. When we reach larger values, for example, from 10 to 11, let's take a look. It's 226.5. The rigid rotor is 227.48, while the non-rigid rotor is much, much closer to the experimental value. You can see that the non-rigid rotor really gave values or predicted values very close to the experimental values. In this slide, we try to find a relationship between the angular velocity omega and the frequency of transition nu. So the angular velocity omega has a unit of radians per second or second minus 1, which is the same as the unit of frequency, which is hertz or second minus 1. So both of them have the same unit, so there must be a sort of relation between them. The rotational energy, as we have seen for a rigid rotor, E, it's equal to half I omega squared. And if this rotational energy is manifested by the radiation, so it will be given as E equals h nu. Then, equating E equals E, we will get omega squared equals 2h nu over I. So this is the relation between the angular frequency and the frequency of radiation for a given transition. Now let's see what happens if we replace atoms by their isotopes. What happens to the energy level? So let's consider an example. We have the CO molecule C12 and C13. An important difference between C12O16 and C13O16 is that C13O16 has a higher mass. When the mass is higher, that means the moment of inertia is higher, I is higher. If I is higher, that means the rotational constant V is lower. If the rotational constant V is lower, that means the rotational levels are closer. So as you can see from the figure, the energy levels of CO for C13 are much closer than the energy levels of CO for C12. And if the energy levels are closer, that means the lines on the spectrum are closer, simply because V is smaller. Up till now, we have studied absorption spectra of rotation. We have another type of spectra or spectroscopy called Raman spectroscopy. This spectroscopy is also valid for rotation. We have seen that for absorption spectroscopy of rotation, only heteronuclear diatomic molecules have rotational spectra. So, using rotational Raman spectroscopy, we are even able to see a spectrum for homonuclear molecules. So, let's see what is a Raman spectroscopy, and in particular a rotational Raman spectroscopy. Raman spectroscopy measures the frequencies of photons scattered from a molecule. These scattered photons may either have an increase in frequency with respect to the incident photons. In this case, they give rise to anti-Stokes lines in the spectrum, or the scattered photons may have a lower frequency in comparison with the incident photons, and in this case they will give rise to Stokes lines in the spectrum, or these scattered photons have the same frequency as the incident photons, and in this case they will give rise to Rayleigh Rayleigh line. Give rise to Rayleigh line. It's a single line. So this process or Raman spectroscopy can be understood as if the molecule is being excited by the incident photon. It's going up to a higher energy level at a certain state, to a wide range of states represented here by the shaded band. So in the case of an anti-Stokes, you can see it starts from this level here. So it goes up and then it goes down to a lower level. By that it is emitting a photon with higher frequency, photon with higher energy in comparison with the incident photon. In the case of a Rayleigh line, you can see that if the Raman spectroscopy measures the frequencies of photons scattered from a molecule. A scattered photon may either have an increase in frequency with respect to the incident photon or in comparison with the incident photon, a decrease in frequency or the same frequency as the incident photon. If the scattered photon has an increase in frequency, in this case, we observe anti-Stokes lines in the spectrum. If it has a decrease in frequency, we can observe Stokes lines in the spectrum, and if it has the same frequency as the incident photon, we observe a Rayleigh line. It's only a single line. How to understand this process? It can be understood as if the molecule is absorbing this incident radiation and it's moving from a certain level to a higher range of state, where it is here represented by a shaded band. These are a wide range of state. So as you can see, this is the incident radiation. Our molecule belongs to this level, so it moves up to this range of states, and then when it goes down, either it goes down to a lower level in comparison with before, which gives rise to anti-Stokes lines, or it goes back to the same level as above, emitting or scattering a photon with same frequency as before and gives rise to Rayleigh line, or it goes back to a higher energy level and it scatters a photon with lower energy, lower frequency, and gives rise to Stokes lines. How is the arrangement of this Raman spectroscopy done? Raman spectroscopy or its arrangement is different from the absorption spectroscopy. One main difference is that the source, in the case of an absorption spectroscopy, has a wide range of frequencies. When photons of different frequencies hit the molecule, some of them are absorbed, and thus we get our absorption spectrum. And we look at the frequencies that were absorbed and we know what we have to do. In a Raman spectroscopy, the source is usually a monochromatic light. It is a laser light with a single frequency. Emitted photons are directed towards the molecule, so when they hit the molecule, they are scattered. The scattered photons now have different frequencies in comparison with the incident frequency, and these frequencies are detected and the Raman spectrum is obtained. Let's look at this arrangement for Raman spectroscopy. We have here the source. The source emits the light. This is a laser beam. It passes through a lens. Then there's a mirror or a curved mirror that contains a small hole. The light continues flowing through this hole and it reaches the sample where our molecules are found. The photons are scattered by the molecules, and when they are scattered in different directions, they are gathered all by the curved reflecting mirror. They are gathered towards a monochromator, and the monochromator analyzes the frequencies of the obtained photons and then sends them to the detector. The Raman effect is based on the inelastic scattering of photons by a molecule, which causes a change in the energy of the molecule. This energy change results in the emission of a photon with a different frequency than the incident photon. For a molecule to be Raman active, it must have a polarizability that varies as function of molecular orientation. What is a polarizability and how it will vary with molecular orientation? Let's take a look on this figure aside. This distortion caused by the presence of the molecule inside an electric field is determined by the polarizability. So the distortion of a molecule in an electric field is determined by its polarizability given the symbol alpha. So if the strength of the field is E or epsilon, then the molecule acquires an induced dipole moment. So we have something that has been created, which is not permanent. This is induced equals mu equals alpha E or alpha epsilon, corresponds to the electric field, in addition to any other permanent dipole moment in it. So this distortion is determined by the polarizability. In some molecules, if we change the direction of the electric field, the distortion alpha will change. We'll get nu mu equals nu alpha times E. In this case, we say that the molecule is anisotropically polarizable. If the same distortion, same alpha in both cases, then the molecule is isotropically polarizable. For a molecule to be Raman active, it must have a polarizability that varies as function of molecular orientation. The anisotropic polarizability is required to produce a detectable Raman scattering signal. In a Raman experiment, the incident photons interact with the electrons in the molecule and cause its electron density to oscillate. This oscillation leads to a change in dipole moment and polarizability, which is dependent on the orientation of the molecule. If the polarizability did not vary with the orientation, the molecule would be unable to give rise to Raman signal. Therefore, the anisotropic polarizability is essential for Raman scattering and enables the detection and the identification of molecules based on their unique spectra. Now, all linear molecules and diatomics, we are talking about diatomics, homonuclear and heteronuclear, are or have anisotropic polarizabilities. So all of them have rotational Raman spectra. So they are rotationally Raman active. So the specific rotational Raman selection rules are delta J equals 0 plus or minus 1. We won't talk about the origin of these selection rules because they are not required in this course, but we are only just going to discuss the spectrum rapidly. First, delta J equals 0 transitions do not lead to a shift in frequency of the scattered photon in a pure rotational Raman spectroscopy. So there's no change in frequency. The frequency of scattered photon is the same as the frequency of incident photon, and this contributes to the Rayleigh radiation, which is a line in the middle. We will see it in the upcoming slides. We can predict the form of Raman spectrum of a linear rotor by applying the selection rule delta J equals plus or minus 2 to the rotational energy level. Now, when the molecule makes a transition with delta J equals plus 2, the scattered radiation leaves the molecule in a higher rotational state, so the wave number of the incident radiation, initially nu I bar, is decreased. These transitions account for the Stokes lines in the spectrum. So if our molecule is in a certain level J and then it is hit by an incident photon, it will absorb this photon, it will move up to a higher energy level, and then it will emit a photon, this is the scattered photon, by going back to the level J plus 2. The molecule has started with an energy level J, and upon scattering a photon, it ended up with a higher energy level J plus 2. So delta J equals plus 2. How to find the wave number of this scattered photon. So as you can see, the wave number of this photon, this is the scattered photon, and this is the incident photon. This is the incident. So the scattered photon, it's obvious that the wave number of this one, this is the scattered photon, this is the scattered, and this is the incident. There remains the difference between the energies before and after. So, or the wave numbers before and after, because you are trying to find the wave numbers. So the upper one has a wave number fj plus 2, the lower one has a wave number fj. So simply, we've got nu I equals nu bar s plus fj plus 2 minus fj. So you can see we have the same formula as before. So nu bar, which is the wave number of the scattered radiation when the molecule starts from a level J and ends up with a level J plus 2, it's equal to nu I. Nu I is the wave number of the incident radiation, Fj plus 2 minus Fj. Okay, so this is the energy difference between the levels before and after of the molecule, and this is equal to B 2J plus 3. So simply Fj equals B J plus 1, and Fj plus 2 is equal to B bar J plus 2. We're adding 2, J plus 3, which is equal to B bar. We have a J squared plus we have 6J, and we have 5J plus 6. So let's subtract them. F bar J plus 2 minus Fj. We will get J squared minus J squared. This cancelled. 5J minus 1J, it is 4J. 6 minus 0, we have no. Okay, so plus 6. You will get, take 2 out, 2 B bar, 2J plus 3. So here this formula gives the wave number of the scattered photon in the case of the Stokes lines. You can see that the wave number is smaller than the wave number of the incident radiation. The Stokes lines appear to low frequency of the incident radiation and at displacements 6b, 10b. So if we substitute J equals 0 for a transition between 0 and 2, we will get the difference 6b. And then 10b if we substitute for J equals 1, and then 14b, etc. So you can see that the distance between two successive lines will be 4b. In absorption Raman spectra, it was 2b, and here it is 4b. Now, when the molecule makes a transition with delta J equals minus 2, so it's the same idea as above, but the molecule, let me erase all ink. So the molecule starts from a certain level J, and then it absorbs the incident photon, so it goes up to a certain level, and then when it goes back to a lower energy level J minus 2. So in this case, the emitted photon or the scattered photon, this is the scattered photon, has a higher energy or higher wavelength than the incident photon. So this is a nu I bar, this is a nu bar. So this has an energy Fj, this has an energy Fj minus 2. You can see that nu I plus Fj minus Fj minus 2 is equal to nu bar. So we will get this form. This must be here a plus. So it appears clearly that the anti-Stokes lines have a higher wave number in comparison with the incident photon. Now let's take a look on the shape of a rotational Raman spectrum. We have seen in the previous slide that for Stokes lines, let me write it here, for Stokes lines, delta J is equal to 2 plus 2. And we've got nu bar, the scattered frequency when the molecule moves from a level J to J plus 2, it's equal to nu I, which is the incident wave number, minus 2b to J plus 3. So if J is equal to 0, then nu bar is equal to nu I minus 6b, b bar for sure. If J is equal to 0, we mean J equals 0, there is a transition from 0 to 2. So when J is equal to 1, nu bar is equal to nu I minus, substitute 1 in J, you will get 2 plus 3, 5 times 2, 10, so minus 10 b bar. This is a transition from 1 to 3. And then J equals 2, then nu bar is equal to nu I minus, substitute 2 for J, 2 by 2 is 4, plus 3, it is 7 times 2, it's 14, so it's minus 14 b bar. This is a transition from 2 to 4. So where are Stokes lines? Here are Stokes lines. These are Stokes lines. If you look at the arrows here, we have a transition from a lower level to a higher level. أول واحد هو from 0 to 2. ثاني واحد هو from 1 to 3. ثالث واحد هو from 2 to 4. هلا, what's interesting it's that the distance between two Stokes lines, the distance between any two Stokes lines, consecutive Stokes lines, is 4 b bar. You can prove it. Just try to subtract the frequency of two successive lines, يعني the j plus 1. It's easy and it's very clear here. You can see that the difference between these two is 4 b bar. The difference between these two is 4 b bar, and etc. It will be the same difference. Now let's see the anti-Stokes lines. For the anti-Stokes lines, delta J is equal to minus 2, and we have found that nu bar, when the molecule goes from J to a lower level J minus 2, it's equal to nu I bar plus, it was 2b bar to J minus 1. So if we substitute for, we can't go for sure for J equals 0 because there's no level minus 2. We'll start with J equals 2. So if J equals 2, in this case, it corresponds to the variation from a level 2 to a level 0. And the nu bar will be equal to nu I bar, substitute for J2. You will get 2 minus 2, it's equal to 4 minus 1, 3 plus 6 b bar. So we can see that if this is a nu I, the first one here will be nu I minus 6 b bar, and the first one from this side is a nu I bar plus 6 b bar. Now if J equals 3, which is a transition from 3 to 1, then a nu bar is equal to nu I bar plus, substitute for J3, we are substituting for J3, so we get 6 minus 1, 5 times 2, it is 10, so it's 10 b bar. And again, if J is equal to 4, this transition from 4 to 2, you will get a nu bar equals nu I bar. Again, substitute for J, substitute instead of 3, 4. You will get 4 times 2, 8, minus 1, 7. So 7 times 2 is 14, 14 b bar. So the next one has a frequency nu I bar plus 10 b bar, etc. So the difference between two successive anti-Stokes lines is also equal to 4 b bar. Now the line in the middle, this one, corresponds to Rayleigh line when the frequency of the incident photon is equal to the frequency of the scattered photon, and it lies, as you can see, at the frequency nu I. So here for the anti-Stokes lines, one more note, corresponds to the case when the molecule moves from a higher level to a lower level, from J to J minus 2. As you can see, the first one corresponds to the case from 2 to 0, then from 3 to 1, then from 4 to 2, etc. Okay, once we are able to calculate the separation between two consecutive lines, Stokes or anti-Stokes, it is 4b. Then we are able to calculate b. Then we are able to calculate I, and once we calculate I, we are able to deduce the internuclear distance between the atoms of the molecule. So this is exactly the same as we used to do in the microwave spectroscopy or in the absorption spectroscopy, where the difference between two consecutive lines was 2b instead of 4b. Let's check this example. Predict the form of the rotational Raman spectrum of N2 for which B bar equals 1.99 cm minus 1 when it is exposed to 336.732 nanometer laser radiation. So he's giving me the wavelength of the incident radiation or the incident photon. He's giving me B bar and he's asking me to predict the form or the position of the peaks, the position of the lines in the case of a rotational Raman spectrum. So we know that we will get Stokes lines, anti-Stokes lines, and the Rayleigh line in the middle. The Rayleigh line in the middle corresponds to a wave number which should be calculated. We have the wavelength lambda. So to calculate a nu I bar, so nu I bar it's simply 1 over lambda. You just substitute for lambda and you will get 29697.2 centimeter minus 1. Don't forget to change units, okay, to get the answer. And now we have to find the frequencies of the rest of the lines. I've already explained them now. I want to re-explain them again. For Stokes lines, where we have delta J equals plus 2, yani J equals 0 goes to 2, J equals 1 goes to 3, etc. So here nu bar equals nu I bar. It was minus 6b bar. So this was the first one. We have nu I, we have b bar, just calculate it. So here nu bar will be equal to nu I minus 10b bar. We have everything. And if we have a transition from j equals 2 to j equals 3, this is j equals 2 to 3, then nu bar is equal to nu I bar minus 14b bar, and then j equals from 3, this is from 2 to 4, and this is from 3 to 5, then we have nu bar equals nu I minus 14, it's plus 4, it is 18 b bar. So just substitute and you'll get your wave numbers. So it's easy. Okay, once you get your wave numbers, you can get your lambdas. So again, just if you have a nu bar, you can calculate lambda. So lambda equals 1 over nu bar. Just check for the units. And for anti-Stokes line, we started with j equals 2 because as you know, we can't start with j equals 0 because we can't go down in this case. So we start only with j equals 2 and then 3. So we showed some of the values of the wave numbers for Stokes, anti-Stokes lines in the case of this molecule. So there's a line in the middle corresponding to Rayleigh line, which is at a frequency equal to the frequency of the incident photon. For anti-Stokes lines, I won't solve them. They are the same command from j equals 2 to j equals 0. A nu bar is equal to nu plus 6b bar. So, and then from 3 to 1, we'll get nu bar equals nu bar plus 10b bar and so on. So just calculate them. They are easy. You have the incident wave number. You have b bar, just calculate the scattered wave number. And you will get these values here. Once you get them, you are able to calculate lambdas below. The last idea talks about nuclear statistics and rotational states. According to Pauli principle, not all rotational levels in a molecule are occupied in the same way. The selective occupation of these rotational states is termed nuclear statistics. So when do we talk about nuclear statistics? We talk about it when our molecule, we talk about diatomic molecule, is homonuclear and it has two atoms that can interchange under a rotation. Interchange equivalently. They are the same. A rotation can interchange them equally. We won't go into details, but just let's understand the whole idea. Let's consider the case when we have a diatomic homonuclear molecule. The atoms of this molecule are identical. Their nuclei have non-zero spin. So how is these spins combined, the spins of the two nuclei? Do both of them have the same spin? Do they have opposite spins? One of them up, others down, both up, both, we don't know. Okay, so some relative nuclear spin orientations favor even values of J, and other combinations of spin orientation favors and odd values of J. So بعض الكومبينيشن من السبينز بتفضل تخلي الاتوم بإيفن J، بإيفن value of J، وبعض الكومبينيشنز من السبين بتخلي الاتوم تكون بodd values of J. So they have found that for a homonuclear diatomic molecule with nuclei of spin I, the numbers of ways of achieving states of odd and even J are in the ratio. So number of ways of achieving odd J يعني قد ايه عدد الستيتس اللي بيكون فيها molecules عندهم J odd over the number of ways of achieving even J, it's equal to I plus 1 over I for half integer spin nuclei and I over I plus 1 for integral spin nuclei. Let's take an example. If we have hydrogen H2 molecule, I it's equal to half. So we will substitute here. We will get half plus 1 over half, because it's a half integer, equals 3 over 2 over half. It is 3 over 1. يعني كل 3 molecules موجودين بodd J بيكون في وحدة molecule بeven J. That's it. This is the meaning of this ratio. Let's try for N2. N2 has its nucleus has a spin 1, so we will substitute here in this formula. 1 over 1 plus 1 is 1 over 2. يعني كل molecule وحدة odd في مقابلها 2 بeven values of G. So due to this, due to nuclear statistics, we can find here in Stokes and anti-Stokes lines high and low intensities due to the occupation. This figure here corresponds to a spin half, for example, for H2 molecule. The rotational Raman spectrum of a diatomic molecule with two identical spin half nuclei shows an alternation in the intensity as a result of nuclear statics. So you can see one up and one down, while back to the previous, for every 3 molecules in the odd J, there's only 1 molecule in the even J. يعني higher intensity lines correspond to transition between odd states. يعني لما ينتقل من odd لodd هو أصلا بينتقل plus 2 أو minus 2، يعني من odd لodd أو من even لeven. The ones that are short correspond to even transition between states from even to even. And as you can see, it's approximately its third size، يعني هي واحد تلته تقريبا، لأنه لكل 3 odd في عندي واحد even، فبالحجم هو تلته.